Good morning and welcome if you are joining us on YouTube and for the rest of the class that is here. Let's talk about what we are going over today and the rest of prep because we are coming to an end very quickly. That makes me sad. But yeah, all right, let's go over some things real quick. Hopefully yesterday went well for those of you that did the homework, or if you're still working on it, no problem. Let's talk about that really quick. Yesterday's homework I made due Sunday at midnight, and today's homework will also be due Sunday at midnight. That's just to give you some extra time if you're still working on those other homeworks. Saturday, tomorrow, I'm going to plan on having office hours, either around 12 or 2. I will send a message out for those of you who need it. I'm assuming that people will probably show up. If not, show up and we can gossip about just about anything that you have questions with, right? I really don't care. But yeah, I'll make myself available for an hour tomorrow because I know your homework, most of your homework's due tomorrow night. So feel free to come in with any questions. With that, other than that, let's talk about a few more things. So I'm starting to get back to grading everyone's homework assignments. So don't worry if it's not graded yet. By the end of this weekend, so by Sunday at midnight, hopefully for those of you that have turned everything in, okay, before then, I will have everything graded with, some feedback for you. I think a lot of people have been asking about solution guides to the homework. It's coming. I might not be able to get like those solutions until quite honestly after prep ends, only because I have I have my final coming up and it's worth 50% of my grade. So I have to really study for that. And it's going to take me at least a few hours to just come up with the solution guide for all the homeworks, but I will still make sure to get that out to you so you can review it before going into your first year at Berkeley. Also, I'm trying to give you feedback through the homework assignment specifically, right? So it's kind of some quick feedback. You can go, oh, okay, let me go check this problem, or so on and so forth. So keep in mind that. Uh, Other than that, I think that's everything. Now let's talk about the rest of the layout for the rest of this class. Today is Friday. We are going to cover 2.8 and 3.1. 2.8 and 3.1, and we're probably not going to get all the way through 3.1 because chapter 3 picks up really fast. It's not a lot of dense material, it's just a lot of formulas and derivative rules. So today we're going to finish up talking about the derivative and how we got to the derivative, what it means, what it represents. Hopefully everyone will be on the exact same page today, regardless of your calculus knowledge and background. So that way, Monday, we're going to go sections 3.1 and 3.2, Tuesday, 3.3, 3.4. If we have to let a little bit fall into Wednesday, like 3.4, if we have to finish up 3.4 on Wednesday, that's okay too. Wednesday, I want to be mostly review, okay? So I'll spend maybe the first 20, 30 minutes just reviewing about everything, chapters 1 through 3.4. And then I'll leave room for questions at the end. And then Thursday, I'm going to give a mock exam during the class, during our class time. So hopefully the goal is on Thursday, right? We'll all show up. I'm going to try and have everyone show up so that way we can start the test at like 9:05, okay? And I'll have it up on the screen. It's not going to be like something you have to stress out about, right? Because I know Friday you're presenting, okay, to Friday's presentations, right? Next Friday. Okay. Yeah. Next Friday's presentations. That's more important. Okay. I don't want everyone stressing out about Thursday. That's why Wednesday is going to be a review. So theoretically, if anything, you're spending at most 1 hour reviewing Wednesday night. Okay. And so I don't want you freaking out about the test on Thursday. You're not getting a letter grade for the class, but I will give a curve for the mock exam on Thursday. And probably by that weekend, you'll have a good idea on how you did with that, if that makes sense. So keep in mind that we're going all the way up to section 3.4. That's going to take us through derivative rules of sine, cosine, polynomial functions, product rule, quotient rule, and oh my gosh, there's one more. Yeah, but basically it's a lot. When will the mock exam be administered? So the mock exam is going to be Thursday during class. So because I have you all up until Thursday, I believe, right? I have you all until Thursday.
13 years ago or whatever.
So
you were ready to go in and just be like,
I think Thursday,
yeah, was
what the plan is, and then from there we will go ahead and grade it. Sorry, I was someone had their mic on, so I was talking and trying to figure that out at the same time. But yes, this is the tentative plan. Do me a favor, If you are a little bit unfamiliar with your derivative rules, or if you have no idea what I'm talking about when I say derivative rules, right? Go ahead and read section 3.1 this weekend. Read section 3.1 and 3.2, okay? Because there's a lot of material. It's not hard, but there's a lot to cover. So when we get to class on Monday, I'm gonna go pretty quickly, okay? Today, I'm gonna slow things down a bit, but yeah, Monday, 3.1, 3.2, it's gonna be pretty busy. So if you need to read those sections in advance, even if you don't understand everything, that's okay. I will try my best to explain it in detail on Monday, but yeah, go ahead and read sections 3.1, 3.2. It's just our derivative rules. And so if you've already seen derivative rules, no worries, it'll be a good brush up. So other than that, any questions for me before we jump into today? And yes, my coffee maker was fixed yesterday afternoon, so I have my coffee back this morning. I'm a very happy individual. And awake. Yesterday, oh my gosh, I was struggling yesterday morning. Not sure if you could tell. You're like, yeah, Zach, you weren't talking as fast. You're right. All right, with that, I'm going to go ahead and jump right into section 2.8 today. Let's finish up here. Let me make my screen brighter. Perfect. Let's go here. All right, so I already wrote some in advance. Okay, let's talk about what we went over yesterday. Yesterday, we went over the precise definition of the derivative. Okay, it's that long equation looking limit up there. Okay, and all we said was basically this, right? We took the limit as x approaches h, sorry, as h approaches 0. Oops, caught my mistake there. Oh no, what's happening? There we go. The limit as h approaches 0, okay? So if you remember from yesterday, we basically said we have 2 points, okay? This is the point at h, right? This yellow one. And this green dot, okay, that's the point x, right? X equals 2 in this case. So we said, well, so yeah, h is approaching 0. But all this basically means is h is getting closer and closer and closer, right, to a singular point, okay? So remember, we talked about the tangent line, right? We said the tangent line passes through it doesn't pass, it touches that singular point, right? So theoretically, right, if we were to take the slope of a singular point, right, rise over run, we would get 0 over 0. But if we take the limit as it approaches that, right, we can find that approximate value. We can find the slope at that point. We've been talking about that for the past few days, so hopefully that makes sense. But in case it doesn't, I wrote it up here, okay? So we said the slope of the tangent line m, right? The slope of the tangent line m is just the derivative, right? It's the derivative of our original function, okay? And the way that we calculate that out, the long way, is this long looking limit equation right here, okay? I gave you a homework problem on it yesterday. If you attempted it, cool. If not, don't worry about it. We're actually gonna go over it today, so make sure you take notes so that way you can submit it and it looks wonderful. Let me just draw this out. Okay, so we have the point x equals 2. Okay, so this is the point right here, this green dot 2, 4. So if I wanted to find the tangent line, right, I just draw a line through it like, oh, well, my eraser. Okay, like that. All right, I'll take that. That's pretty good. That's pretty decent. Okay, so everyone can see, right, how that tangent line like touches that singular point right there at the point x equals 2, right? This is just a line. We know that we can calculate the slope of that line. How do we know what the slope of that line is? Well, we have this equation right up here. We have m is equal to the derivative of f prime of x, okay? So the derivative f prime of x is simply, we take the limit, blah, 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 we calculate it out. Cool. In our notes yesterday, we took the graph f of x is equal to x squared. That is the black graph. Hopefully you can see that's f of x equals x squared, okay? We plugged it into the limit equation, so if you're wondering where I got the derivative f prime of x equals 2x. That's from our notes yesterday. Okay, so that should be in your notes. We calculated out, we said, okay, our derivative of f prime of x is equal to 2x. Okay, that's what we got. Our final answer was f prime of x is equal to 2x. Now, I want to know what is m at the point x equals 2, right? When x equals 2, what is the slope, right? What is the rate of change, right? Slope, rate of change, it means the same thing. I'll be more precise. I'll say, what is the instantaneous rate of change at the point x equals 2 of the black graph, okay? Well, we said that the slope is equal to f prime of x, which is equal to 2x. Well, at the point x equals 2, right, we plug in 2 to our derivative equation. 2 times 2 is equal to 4. So that tells us our rate of change at the point x equals 2, it's 4. And if we look at this green, I'm going to erase this real quick. If we look at the green line right there, we can see how that green line kind of has a pretty steep slope, and that slope is 4 at the point x equals 2. Now, what if we wanted to find the point at x equals 3? Does everyone see that? That's the point x equals 3 right there. So let's call this x equals 3, right? On our original graph, right, f of x equals x squared, what if I said, okay, what is the derivative, what is the rate of change at x equals 3 for our original function f of x equals x squared? Well, you can sort of see the same process here. I draw my tangent line like this. Oops, that's horrible. Let me try this again. Okay, pretend those touch right there, okay? That's at the point x equals 3. Already, we can tell one thing before we even calculate it out. The slope of the yellow line, right? The slope of the tangent line at x equals 3 is steeper than the slope of the tangent line at x equals 2. Intuitively, that makes sense. Why? Because remember, x squared is an exponential, so it gets infinitely more and more large going off to infinity, right? Think back to our slide analogy where you start at the very top, you're dropping super fast, then it starts to peter out right towards the end there, right? So now let's go ahead and calculate that out. We now have the point x is equal to 3, okay? X equals 3. How do we know what the slope is at the tangent line? Very simple. F prime of x is equal to 2x. F prime of x is the slope of the tangent line. So m is equal to 2x. In this case, we plug in x equals 3. 2 times 3 is equal to 6, okay? So this yellow line has a slope of 6, and this green line has a slope of 4. Intuitively, it should make sense. Graphically, that's how we explain it, okay? So again, all I did was I plugged in the x plus h into the f of x equals x squared equation, right? Factored it out, cancel the h's. What's left over as h goes to 0, f prime of x equals 2x. That's in the notes yesterday. If you're still having trouble with that, go back to the YouTube videos, which, by the way, are all posted, including your homework example. I forget which one, but it was the one that we talked about in class with e to the negative y exponents. Those are also up on the YouTube channel. Go check that out, like and subscribe. I have like 23 subscribers. Awesome. Half the class. Cool. But yeah, those are all uploaded too. So let's go ahead and move. Before I move on, any questions? Any questions? Or does this make sense to everybody? It makes sense to everyone. Cool. That's really good. That's exactly where I want us to be. That is awesome. So we're starting to understand what a derivative represents. It represents the instantaneous rate of change. How do we find it? We simply draw a tangent line. What is the slope of that tangent line at that point? Boom. That's the derivative. Cool. Let's talk about graphical analysis. Let's draw again our graph of f of x equals x squared. I'm sorry that we have to deal with this. Oops. I know that we have been dealing with this graph a whole bunch, but we're still going to be doing it. Why? Because it's an easy, quick example, and I think it's really straightforward and logical. So everything should make perfect sense. Okay, this is why f of x is equal to x squared. Cool. All right, let's graph f prime of x, right? We said f prime of x is equal to 2x, right? F prime of x is equal to 2x. So the derivative, right, is equal to 2x. Do we know what that graph looks like? Sure. Let's go ahead and plot it, right? Let's plot it and let's see if we can figure out some things here, okay? Let's plot it like this. Let's do something like this. Yeah, All right. Okay, so what did I do here? I graphed our original function and I graphed the derivative of that function, okay? Again, remember, the derivative f prime of x, that is equal to the slope, right? That is equal to the slope of the tangent line at a given point. The slope at a tangent line, right? The slope, comma, m, that does not look like an m. What is that? That is an m. Okay, f prime of x is the slope of the tangent line at that point. Let's see if we can let's see if we can analyze some things here. So let's go ahead and pick a point on our graph of f of x equals x squared, our original graph. Okay, let's say this is the point x equals 1. Okay, so this is 1 comma 1 on our graph, right? Question: what is the slope at the point x equals 1? Easy. We take our coordinate x equals 1. Now we plug it into the graph of f prime of x, right? So 2 times 1 is just 2. So the slope at 1 is simply m equals 2. All right. Is it positive or negative 2? It's positive 2. M is equal to positive 2, right? So again, right, we're right here. Or f prime of x is equal to 2x. Plug in 1, we get a value of 2, like that. All right, easy enough, pretty straightforward. Yeah. Cool. Let's now talk about the slope at -1. Okay. This is now x equals -1. All right. Oops, sorry, -1. Okay. So when x equals -1, okay, we can see our green point is right here, right? But we want to find the slope at that point, right? We want to find the slope of the tangent line, right? We want to find the slope of this line right here at the point x equals -1. What do? Plug it into our derivative equation, right? Because that'll tell us the slope. So we have f prime of x is equal to 2x, right? 2x where x is equal to -1. All right, see how I did that? Just plugged in -1 for x. 2 times -1, that gives us the value of -2. So we go to our derivative graph now, okay? So this is at the point x equals -1, and we get the value all the way down here, right? Or our y value is -2. Does everyone see how I got that, right? Does anyone not see how I got that? Okay, good. So let's see if we can I go over it? Yeah, let me go over that one more time, okay? 2 things. 1, this is the graph. This is the graph. The black graph right here, that is f prime of x, okay? That is the derivative of our graph, of our original graph, which we said our original graph is f of x is equal to x squared, okay? That is this yellow graph right here. Now, all I did was I said, let's pick a point on our original graph, right? In this case, for this example right here, oh, now we have no point. There we go. I said, let's pick the point 1, okay? X equals 1. At x equals 1, okay, we're right here on our original graph, right? You plug in 1 to x squared, right? You get the point 1 comma 1. I said, what is the slope of the tangent line at that point, right? If we draw our tangent line that looks, oh my gosh, eraser, I'm so sorry. If we draw our tangent line like this, let me delete this arrow. If we draw our tangent line like this, okay, I want to know what the slope is at that point. What is the rate of change at that instantaneous point? Well, we graphed, okay, we said at the point x equals 1, we graphed our derivative equation, right? So we plug in 1 to the derivative equation. 2 times 1 is positive 2. Boom, positive 2 is right here, okay? The slope of the tangent line at that point is positive 2. Now, I said, let's go ahead and pick another point now. Let's pick the point x equals -1. Boom, x equals -1. F of x is equal to 1, right? -1 times -1 gives us positive 1. So we are right here on this graph. Now, I want to know what is the slope at this point, right? Because they're different. What is the slope of the tangent line at this point? In other words, the tangent line looks something like this. What is the slope at that point? All I did was I plugged in -1 to our equation, right? -1 times 2, that gives us a value of -2. So that's how I got the value of -2 for the derivative equation, right? Now, we go to the point -1 comma -2, right? because I plugged in the point -1 and it gave me a value of -2. So it gave me this point, right? Our derivative equation gave us this point, -1, -2. So I go ahead and plot that. I can see down here, okay, here's -1, here's -1, -2, boom. See how that line or that point ends up on our graph of the derivative equation, right? All I did was graph the two separate lines, the original equation and the derivative equation. So it's just showing us the values graphically. That's all we're doing here, okay? Now, what is this information telling us? Okay, well, let's look at our, I'm going to go ahead and rewrite it over here, okay? Let's look at our origin for a second. Let's go ahead and draw just the derivative graph, okay? This is the derivative graph, okay? This is the origin 0, 0. This is our y-axis, this is our x-axis, okay? So this is f prime of x. Okay, so when f prime of x, oops, is that a t or an f? It's neither in this case because it doesn't look like anything. F prime of x, okay? When we have f prime of x, can someone tell me something? This is also equal to our slope, right? This is m, the slope of our tangent line, okay? At the point, let's start here. Between 0 and infinity, who can tell me something about this graph? All of our values are what? Are they positive or negative? Positive. Yeah, awesome, right? So based off of this graph, okay, that is telling us that from 0 to infinity, I'm not gonna include 0, right? So from 0, non-inclusive, okay, to infinity, right? All of our values for the derivative graph are positive. What does that mean? That means that all of the slopes, okay, f prime of x is equal to m, which is the tangent line slope, right? That tells us that all of our slopes for the tangent lines are going to be positive. What does that mean? That means all of the slopes, literally all of the slopes, like I just said, positive, right? They're going to look something like this. It might be really, really positive. It might be slightly positive, right? But the thing is to remember here is it's positive, right? All of these values, the derivative is telling us that from anything after 0, right? Even 0.00001, it's positive. So our tangent lines are going to look something like that. Now, who can tell me something about from negative infinity to 0? What are those values, right? The value of the derivative, right? We get negative values, right? So in other words, negative infinity, 0, from negative infinity to 0, right? All of our values are negative, right? We said if all of our values are negative, what does that tell us about our slope, our tangent line slopes? Well, that tells us that our tangent lines are going to look something like this, all with a negative slope, right? It might be a very, very slim slope. It might be almost a vertical line, right? But our tangent lines from all the x values that are negative, right? They're all going to have negative slopes, negative tangent line slopes. All of the values to our right, they're going to have positive slopes. What does this mean? Let's look at our original graph again, okay? Here's the original graph. Let me graph it. Let's go ahead and basically write out what we just talked about. We said this is the point 0, 0, right? This is positive x values, okay? This is negative x values. Let's go ahead and graph some tangent line slopes, okay? If we have a point here, the tangent line looks something like that. Is that positive or negative? Is that a positive slope or negative slope? It's positive, right? You don't have to say that in the chat, right? We can clearly see it's increasing. All right, same thing here. Let's pick this point and something like this. It's a little less positive, right? But nonetheless, it's still positive, okay? Let's say we picked a point way like beyond our graph, right? It's like all the way up here, okay? It's just about a vertical line, but it's still positive, right? I think everyone sees where I'm going with this. So now let's go ahead and let's pick some points to the left. Let's pick some negative x values on our graph. Let's say x equals, invisible. Let's say x equals -1, x equals -2. Let's draw the tangent lines at those points. Here we go. Boom. Right? And boom, just like that. Sorry, I'm not on point today. Maybe it's because I'm drinking coffee and I'm not able to draw effectively because my hands are shaking. It's a love-hate relationship with coffee, I promise you. Anyways, does everyone see how everything to the left of 0, right, on our original graph, we get negative slopes for those tangent lines, right? We said f prime of x is equal to m, right? M is simply the slopes of those tangent lines. Everyone can see that we're getting negative values to the left of 0, and we're getting positive slopes to the right of 0. Okay, what about at x equals 0? Let's talk about this. Does anyone have any questions for me? Hopefully that should make sense, right? We said, okay, this is what our derivative graph is telling us. Let's see if it checks out in real life. We just proved that it does. Cool. Let's talk about the point x equals 0, okay? This is at the origin here, at 0, 0. Question. The tangent line at this point, is this the tangent line at this point? Yes or no? Is that a tangent line? No, no, no. Everybody's saying no. Really? I thought I was right. I'm kidding. Why? Because it's going through the point. Remember, we said that the tangent line, it's hard to explain, but theoretically, right? It touches that point. It doesn't go through it. It touches it at a singular point. So how do we write this then? How do we not have it go through that entire point? Well, we have to draw it completely flat, right? Boom. Okay, that was pretty good. See how we touch it, but we don't go through it, right? I have a question for everybody. What is the slope of this tangent line? This is section 2.7, 2.8, okay? Right, what is the slope of the tangent line at this point? Cool, everyone is saying 0, wonderful. What is this telling us? This is telling us two things. This is f prime of x, right? The slope here, right, we have no rise. This is our run. It is a flat line. Flat lines have no slope, okay? So at the origin, at x equals 0, okay, we have a slope of 0. Pretty much parallel to a single point, right? So this is what we figured out. We said at x equals 0, the slope is equal to 0. Let's go back to our derivative. Let's go back to our derivative equation real quick, okay? We said f prime of x is equal to 2x, okay? Does this check out? When x equals 0, if we plug in 0 for x, right? 2 times 0 is 0, right? Our slope, our derivative, f prime of x is equal to 0. What is this telling us? That is telling us one of two things. One, that tells us that we calculated our derivative correctly. Cool. That is also telling us that this is giving us an accurate description. Well, yes, let's talk about this really quick. That means if we have our original graph, okay? If we have our original graph and it looks something like this, when you have a change in concavity, okay? When you have a hill that looks something like that, the tangent line at that point is always going to be 0, okay? So whenever, let's say our derivative looks something like this, okay? Let's say we found an original function. I could actually find it if I want to. F prime of x is equal to x plus 2 and x minus 2, okay? So let's just say, I'm gonna get rid of this really quick. Let's just say, hypothetically, this is a graph of some function, okay? We don't know what the original function looks like, but we were given the derivative equation of it, right? When we set it equal to 0, right, we get the points x equals 2 and x equals negative 2, okay? What is this telling us? We just proved it. That means at the point x equals 0, okay? So this is f of x here. Okay, f of x is the blue, so I'm going to draw the blue graph as f of x, okay? Let's go to the point x equals positive 2. Boom, we're at positive 2 right here, okay? When we set the derivative graph equal to 0, okay, that means that we have a hill here, okay? It could be above, okay? It could be negative, right? We aren't sure just yet, right? But we know for a fact at the point x equals 2, okay? There has to be a shift in concavity, or in other words, there is a plateau, right? How do we know? Because when we draw the tangent line at this point, okay, I'll draw it in red here to match the color coordinate, okay? If we take this point right here and we draw a tangent line through it, does everyone see how the slope of that line is 0, right? Okay, good. Likewise, at the point x equals negative 2, this is the point x equals negative 2 here, okay? We know we're gonna have another hill, right? The original graph is gonna have something that looks like this. Why do we know that? Because when x, we look at our original derivative equation, right? We look at our f prime of x, we said that when we set it equal to 0, sorry. So when we set this equal to 0, right, we get x is equal to +2 and x equals -2, right? So when x equals -2, right, you can see right here, -2 plus 2 is 0. 0 times anything is just 0, right? So that means that at x equals -2, our slope of the tangent line is also 0, okay? Same thing. It could look like this. Oops, now it looks like nothing. Cool. This is x equals -2, okay? We draw our points. We draw the tangent line through that point. We see now that there has to be that plateau there in order for the tangent line to have a slope of 0. Okay, here's where I'm getting with this. No, I'm not getting into the absolute like tests yet. That'll come. Right now, I'm just talking about how we can look at graphs and how we can analyze those graphs and figure out which one is the derivative and which one is the original, okay? So I'm gonna draw 2 graphs, all right? You've never seen them before in your life. You've never, ever, ever seen them before in your life, ever. It's the first time you've ever seen it. It's a miracle. Question. Which one is f of x? Tell me in colors, which one is f of x and which one is f prime of x? Okay, is f of x equal to the red graph or yellow graph? Is f prime of x equal to the red graph or yellow graph? Tell me right now. All right, f of x is yellow, f of x is yellow. Hello is f of x. Hello. F of x is yellow, cool. F of x is yellow, yellow is f of x. Yellow, I'm getting an f prime is red. Awesome, okay. Hopefully everybody sees this, all right? How do we know? We said, all right, this red graph right here, it's negative values. What do? We look at the tangent points right here. Do these all have negative slopes? Yes, they do. Okay. Now, once we get past 0, right, we look at the red graph again. We go, okay, these are all positive values. What is that telling us? That is telling us that these points right here have positive, right, tangent slopes. Cool, that checks out. What about at the point x equals 0? Well, it's as simple as this. Okay, pretend this passes through the origin here. Okay, at x equals 0, okay, the red graph equals 0. Does everyone see that, right? So the red graph, right? Sorry, I'll draw that in red. The red graph, right? For the red graph, when x is equal to 0, okay, the actual value of the red graph is 0, okay? What is that telling us? That is telling us that at x equals 0, boom, we have a horizontal line for the yellow graph. That tells us that the red graph, right? The red graph is equal to f prime of x, okay? So I'll write it in here. And the yellow graph is our original graph, okay? Let's talk about these graphs now. Sorry, there's 2 questions in the chat. Is the lowest power graph the derivative and the highest power graph the original? Yes, yes it is. However, you're going to get a homework problem that is going to be giving you multiple graphs. So you're going to have to be a little bit, in other words, right? I'll make it a little bit tricky on you, but hopefully everyone is starting to understand how we can look at the graphs and figure out which one is the original and which one is the derivative, right? So this is all section 2.8. Let's cover one other thing really quickly. Yeah, let's cover this really quick. Okay. Graphs that look like this, or graphs that look like this. Okay. Or like step functions. Okay. All these types of graphs, they are technically, these are not differentiable. Can we take the limits from the left and right? Yes. Are they differentiable? No. In other words, let's say this is the point x equals 2, right? Pretend that all of these match up, okay? you're going to get your f prime of x is going to be something like this, is equal to 1 over -2 plus x, right? So you can obviously see when we plug in x equals 2, we get 1 divided by 0, right? It's not differentiable. So just keep in mind, right? If your derivative graph has stuff in the denominator, okay, at that point, just know the graph is going to look something like this. There could be a vertical asymptote, right? Just kind of keep that in mind. I just wanted to cover that really quickly. If that doesn't make sense, don't worry. When you're doing problems, okay, you're going to see really quick at the point x equals 2, you go, wait a minute. You'll get a question. It's like, is f of x differentiable? Okay, I'm just going to write diff. Okay, is f of x differentiable at the point x equals 2, right? You take f prime of x, okay, you go, oh, f prime of x is equal to 1 over -2 plus x, okay? You're gonna, sorry, that's a plus sign, okay? You're gonna plug in your value of 2, right? You're gonna get 1 over 0, and you're gonna go, no, it is not differentiable at the point x equals 2. That's all I wanted to cover. Cool. Let's go over some, so we're gonna keep talking about graphs in just a second. Let's talk about, let's talk about notation really quickly, okay? I said we have f of x here, okay? And we said f prime of x is the derivative, right? When I say take the derivative, sorry, derivative, okay, I'm just gonna pretend that I didn't just spell very illegibly. Derivative. We said f prime of x is the derivative. Okay, now I forgot how to spell. No, I didn't. Derivative. Boom. Okay, which is equal to, yes, an e. It's early, give me a break. That's equal to the slope of the tangent line, and we've been talking about it. Hopefully you know what the derivative represents now, okay? But f prime of x is the derivative. We can label the derivative as other things. We can call this dy dx, right? We can also call it the derivative of, which is just simply d dx of f of x, okay? Let me rewrite this a little bit clearer, okay? This is just notation. We're not learning anything new here, okay? F prime of x is equal to the notation dy dx, which is equal to the notation of d dx of f of x, where f of x is any function, so it could be g of x, g of whatever else, right? All of these, okay, if you see these different types of notation, all it means is the derivative, okay? This is the derivative of f of x. This is the derivative of f of x, where it's just y equals whatever x is, right? Remember, we can say y equals x squared, f of x equals x squared. They mean the same thing, okay? It's just different notation. That's all it is. D dx of f of x, okay? That's saying we're taking the derivative of f of x, okay? Means the exact same thing. Just wanted to get that out of the way now because unfortunately, when people were inventing calculus back in the, oh gosh, 1700s, was it Newton? Was it Isaac Newton? I don't remember now. One of them. You had Leibniz, you had Newton, you had the other one. They all came up with their own notation for what the derivative should be. And all of the calculus teachers of today and so on and so forth, and everyone in their different professions, they all like to use different notation. We cannot agree, so we just said they all represent the same thing. That's all. So don't get confused if you see dy dx, right? D dx of f of x or f prime of x. All of it represents is just the derivative. Okay, wanted to get that out of the way. Let's talk about some more graphing analysis. I am going to give you the graph of this. I'm going to draw it very poorly. Cool. Boom, like that. I'm now going to give you this graph. This is a blue graph. It is going to look something like this. Boom. Question, which graph is the derivative of the other one? Tell me, which one is the original graph? Which one is the derivative graph? We are waiting in the comments. We're thinking. Blue is the derivative, blue is the derivative, yellow is the original, blue is the derivative, original, blue, ooh, original, blue, yellow, original. Yellow is original. Yellow is original, yellow is original, blue is the derivative. Okay, good, good. Yes, for the most part, that all is sounding correct. Let's talk about it, okay? How do we know which one is the derivative? How do we know which one is the original? Okay, we said for every, we said that when the slope is negative, right? When the slope is negative of the derivative graph, okay, we are going to have the original graph is going to be looking something like that, okay? When the values of our derivative graph are positive, right? When m is positive, okay, our original graph, the tangent lines are going to be something like this, okay? Let's talk about why the blue graph is the derivative graph, okay? Keep that in mind. When m is positive, the values of m, right? The values of f prime of x, when those are positive, we have positive slope. When those values are negative, we should have a negative slope, right? So I can see where this could get a little bit confusing, but there's some key differences here that we have to know, okay? Yeah, I could see where these values are negative. Therefore, we're seeing, okay, all right, I see this right here. This is negative values. All right, we look at this graph right here. We're going, we're saying that this graph right here, these values are positive. Cool, we have some positive slopes. That's plausible, right? That's plausible. But there's some key things here that that make this graph the other way around. Okay, when we have these values right here, these values are negative, right? These values are negative, right? Yeah, these are positive, but these are all positive values. So when we look at the yellow graph right here, we look at this yellow graph, we see that we are still increasing right here. Does everyone see that, right? We're increasing. These are positive slopes, okay? So intuition is telling me, okay, maybe the blue graph is the derivative, right? Because all of the values up here are positive, and we have a positive slope right here. Cool. Oops. Now, this is kind of a bad example because I could see where both graphs look like they both look like they could be derivative, like one or the other could be the derivative, right? So this was probably a poor example of my choice, but I'm going to try and hopefully explain it in a little bit better sense. Okay, again, right here, we still have positive values, okay? We still have positive slopes right here, okay? Do we still have positive values in the blue graph? Yes, we do, okay? So intuition is telling me positive values for the blue graph on the left and right side, and we have positive slopes on the yellow graph on the left and right side. Now, again, this is kind of a bad example. Why? Because we look at the origin, okay? We said this passes through the point x is equal to 0, right? If we look at this yellow graph, okay, we draw a tangent line. We can kind of see how that tangent line is like right at 0, okay? But to answer the question, yes, the yellow graph is the original, f of x is the original. The derivative graph is the blue one, okay? F prime of x. So let's talk about this. If you recall, oops, let me erase this real quick. Okay, those two graphs that I just drew, that was f of x. Sorry, I'll draw this in yellow here so it's not confusing. That was f of x is equal to x cubed. Is equal to x cubed. All right. That derivative graph that I showed you, that was f of x is equal to 2x or 3x squared. Sorry. Oops, like that. F prime of x is equal to 3x squared. For those of you that have taken derivatives for, that makes sense. If you're wondering how I got f prime of x, I used a very, very quick and easy process. So far, the only process you know how to use is simply you take the limit of that horrible looking equation as h goes to 0, right? Of like f of x plus h minus f of x all over h, right? That long equation. And then you get to this point right here. Spoiler alert, that is not what you're going to be doing for the rest of your life. There's a much, much easier way to take the derivatives. Okay, so we talked about graphical analysis. Hopefully that makes sense. If anything, here's the one thing I want you to take away from it. Okay, when you're trying to figure out which graph is the original, which graph is the derivative, okay? Let's say we have a graph that looks something like this. Boom, 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 all right? I already know multiple things. I know multiple things. I know that when I take the derivative of this graph, okay, at this point right here, boom, my derivative graph is going to cross x equals 0, okay? I know, boom, right here, again, okay? It's going to also cross x equals 0. And let's say at this point right here, actually, let me redraw that part. So it's going to cross 0. Let's say it does something like this, okay? Boom, okay? What is this telling me? This is f prime of x. This is f of x. All right. How do I know what those points are exactly? Because I'm looking at the tangent lines at these plateaus, okay? We have a plateau right here. We know that the tangent line has a slope of 0 at this point. Same thing right here, okay? We have a tangent line where the slope is 0. And again, right here, we have a tangent line where the slope is 0. What does that mean? That means when we're looking for the derivative graph, okay, the derivative has to cross the line x equals 0, right? Because when f prime of x is equal to 0, right? When f prime of x equals 0, that tells us that the slope, right? Because f prime of x is our slope of the tangent line, that means the slope is 0, and that checks out. Hopefully everyone understands that, okay? So again, this is f prime of x is equal to 0, and right here, this is the point f prime of x is equal to 0. That checks out. We have our tangent line here, tangent line here, tangent line here. They all have a slope of 0. That's the one thing that I want you to remember about graphing. Cool. I will go ahead and leave that up for like a few more seconds. Sorry. I know that sometimes I go through things without giving you enough time to write it down. If I ever do that, please just tell me to go back. There's a good chance that I didn't erase it yet because it saves up to 12 slides. So I will move on in like 10 seconds unless anyone has any objections. 4, 3, 2, 1. Awesome. Let's move on. So that's what I wanted you to figure out. Now, we have about 10, 15 minutes left. I want to talk about an easier way to find the derivatives. Now, this is why I want you to read up on sections 3.1. And if you can get to 3.2, good. At least get through 3.1 over the weekend if you're still kind of struggling a little bit, okay? Because I'm going to go pretty fast through 3.1 because it's just a lot of formulas, okay? So in your textbook, if it boxes something, just write that down. That's all I need you to do, okay? Just write down whatever is in the box in your textbook. That is section, again, 3.1 in your textbook. Take the weekend, look over it, see what it's trying to say. All right, up until now, this is so that we're starting to get into section 3.1 a little bit, okay? Up until now, we've been having to take the limit as x approaches h, right, of a function of f of x plus h, right? We plug this in, minus f of x all over h, right? Then we said, all right, we have the graph of x squared. We have the graph of x squared here, right? F of x equals x squared. When we take the limit, we plug in all of that stuff, right? F of x plus h, sorry, that is a plus h, okay? We said that f prime of x eventually cancels out, pull out an h over h cancels. I'm stupid. Again, I'm sorry. This is as h approaches 0. I'm so sorry. As h goes to 0, right? The h's cancel out. You plug in 0 for h, boom. F prime of x we're left over with equals 2x, okay? Up until this point, that is how we take the derivative, right? We have to use this long, horrible equation, right? What happens when we get a graph what happens when f of x looks something like this? F of x equals x to the 4th plus 2x squared plus, that is going to take us forever, right? Why on earth would the people who invented calculus make it super hard? Well, because it's calculus. But at the same time, there is an easier way to solve this, okay? I want you to look at the I want you to look at the similarities between our original graph, f of x equals x squared. Okay, that's f of x equals x squared. And our derivative graph, right? F prime of x is equal to 2x, okay? Look at that for just a moment. What's the same? What's different, okay? Does someone want to tell me one thing that's the same in the chat and one thing that's different? Or some similarities or just some sort of some sort of like what do we still have here? Obviously, we still have an x, right? Nobody's typing in the chat. Oh, there's one. Emmanuel, yes, thank you. Okay, so Emmanuel said there's still a 2, right? In other words, this is f of x, we have an x squared here, f prime of x, we have a 2. Okay, awesome. All right, now, that other equation that I gave you, okay, the 2 is the same as the square in the original. Yeah, the exponent decreases. Good, we're figuring out a pattern, right? Let's go to that other example that I gave you, right? I said f of x is equal to x cubed, right? Is x cubed. We said f prime of x, right, was, I didn't prove this, I just told you, f prime of x is equal to 3x squared, okay? Now what's still the same, okay? We can see, all right, the exponent in our original equation is now multiplied in front, right? Does everyone see that? We have the 2 in front here, okay? In our original equation, now it's just multiplied in front. Okay, let's start to develop our formula. Oops. So with that, let me, so we said whatever the exponent is, I'm gonna call it x to the n. Okay, if we have x to the n here, okay, then the derivative is nx, right? So we pull that number, we bring it down in front. I'm gonna rewrite this in just a second. Remember these two equations, okay? I'm gonna go ahead and develop the formula for the easy way to calculate a derivative, all right? Let me go over here. Cool, I still see there's most of us here. Thank you for being here. I know you've probably seen this before. You're like, this is really straightforward. It's still good review, right? So again, this is f of x. This is f prime of x is equal to 3x squared. Awesome. Let's develop our formula, okay? Let's say we have x to the n, right? X to the n could be where n is any real number, right? N is any real number. It's all real numbers, right? If we have f of x is equal to n, then f prime of x is equal to nx, right? Because we see here, if n is equal to 3, then the derivative is simply 3 times that. But what else happens? Okay, look at the exponents. We have a 3 here, we have a 2 here in our derivative, right? The original equation was raised to the 3rd power. The derivative is only raised to the 2nd power. So intuition tells us, right? Yes, n minus 1. Thank you, Claudia. That is absolutely correct, right? That is telling us that we have 3 minus 1, which is equal to 2, right? So we look at our derivative equation. How did we get 2? We subtracted 1 from it, all right? How did we get, all right, think of that other equation, right? F of x is equal to x squared. F of x is equal to x squared, like that, okay? We said f prime of x, when we plugged it into that gigantic limit equation, okay? We said that is equal to 2x. Well, what is 2 minus 1? 2 minus 1 is just 1, right? You can see there's an invisible 1 here. This is technically x to the 1 power. So intuition tells us the derivative is simply this form, okay? Everybody write down this equation. This is imperative. In the blue box, we have the derivative f prime of x is equal to n, right? Whatever our original value was, minus 1 in the exponent. Okay, boom. And I will go over like a few quick examples with that. I heard anybody have questions or anything? All we did right here was we looked at a pattern. We said, you know what? This is f of x, this is f prime of x, this is f of x, this is f prime of x. We said, wait a second, I'm recognizing a pattern here. Let me go ahead and write this pattern out. This is the pattern. I'm about to show you how we use this, okay? Does everyone have this derivative? Yes, this is the derivative of x, right? So this is our original x equation. This is our derivative of that x equation. Now, there are a whole bunch of different derivative rules. This is only for polynomials of degree n. Of just x though? Great question. Yeah, let's talk about that. Does everyone have this written down? I'm gonna move on real quick. I have like 3 or 4 minutes left of your time. I'm gonna use it if you're okay with that. Awesome, okay. I'm going to, yeah, what is the derivative of x? Let's go ahead and work that out right now. Let's go to right here. I'm going to delete this. Boom. Okay. We said I'm going to write our formula up here. Okay. The derivative of f prime of x is equal to x to the n minus 1, right? But the n is multiplied out in front. Okay. What if f of x is equal to 1? Or I'm sorry, what if f of x is equal to x? What do we do, Zach? Well, let's first start out by finding what our n is, right? This is from the generic form of f of x is equal to x to the n, okay? So remember these two equations, right? We have f of x is equal to x to the n. F prime of x is equal to n x to the n minus 1. All right. What is this exponent? F of x is equal to x. What is the exponent on the x? It's just 1. Cool. Everyone's on the same page, right? We can technically say this is x to the 1 power, right? X to the, or anything to the 1 power is just itself, right? We know it can't be 0 because what happens if it's 0? If this were x to the 0 power, this would give us 1, right? We don't want that. We don't want that at all, right? So we know starting out, this is x to the 1 power. In other words, n equals 1, okay? So n equals 1 right here, right? From our f of x equation, let's plug it into our f prime of x equation, right? So we said f prime of x is equal to, in this case, we plug in n equals 1, okay? 1 times x to the n minus 1, okay? So we plug in 1 to the n up here, we get x to the 1 minus 1. What is this telling us now? We have 1 times x to the 1 minus 1. 1 minus 1 is 0, right? So this is x, so this becomes x to the 0 power. 1 times x to the 0 power. Now, we said by definition, okay, we said anything raised to the 0 power is 1, okay? So this is equivalent to 1. We are left with 1 times 1, which is just 1, okay? So the derivative, just to recap here, the derivative f prime of x is just 1. It's a constant, it's number 1. Does everyone see how that makes sense? Any questions? No questions. Awesome. Now, does everyone see how I got that derivative now, right? If not, go back to like the last 5 minutes of the YouTube channel, on my YouTube channel, watch that explanation over again, and it should clear things up for you. All right, I'm gonna go through some things really fast, okay? Let's say we have f of x in this column, right? F of x equals, okay? I wanna know what f prime of x is equal to. Okay, I'm gonna draw this column really quickly. Why? Because you can go back later on and see. Like that. Here's what I'm gonna do. Yeah. Perfect. This is f of x, this is f prime of x. Cool. We have x. We have x to the 6th, x to the 5th, x to the 4th. Okay, so these are all different graphs, x to the 3rd. Okay, what is f prime of x? This is simply 6x to the 5th. To the 5th. This is 5x to the 4th. This is 4x cubed. And just using that derivative rule, this is 3x squared. All right. So these are your f of x, right? F of x equals that. F of x, oh, sorry, I'll use blue here so it doesn't get color or mixed up. F of x equals x to the 6th. F of x equals x to the 5th. F of x equals x to the 4th. F of x equals x cubed. What does f prime of x equal? X to the 5th, right? 5x to the 4th, 4x to the 3rd. Write this down or take a picture of it. Go. Go for it, go for it, go for it. And I will talk about one more thing since I have you for 2 more minutes. It's actually 1 more minute now. And then I'll go ahead and give you some homework. Okay, is everyone okay if I erase this? Anybody not want me to erase this? All right, yes, I can go ahead and erase it. If you don't want me to erase it, say no now. Say no, hurry. 5, 4, 3, 2, 1. It's gone forever. An extra 2 seconds. Okay, bye. It's gone. Yeah, again, that was just really, really quick, easy practice. So you can see, okay, original graph, derivative, original, derivative, original, derivative. using that rule. Now, keep in mind, this is only, you can only use this method. This method only works for polynomials, of degree n. Polynomials of degree n. Should have said that at the beginning. Okay, this rule only applies for polynomials to the degree of x to the n power. Okay, this is the intro to section 3.1. We're going to talk about a whole more different rules in section 3.1, right? And the way you know is, okay, what's the derivative of sine of x? You're like, oh my gosh, I have no idea what the derivative of sine of x is. That's okay. There's a special rule for that too, right? Sine of x is not a polynomial. Therefore, it's going to have its own special derivative rule. But anyways, yeah, this is only for derivatives of polynomials of degree x to the n. Now, one more thing. Let's say f of x is equal to 3x squared. What is f prime of x in this case? Well, that 3 there is throwing us off. Now what do? Okay, same exact process. We bring the 2 down in front. We leave the 3 there. Leave the 3 there, right? Yeah, perfect. This becomes 2 times 3x. Does everyone see how I got that, right? If we just had x squared, then the derivative is simply 2x. But in this case, we have that 3 in front. Leave the 3 there. 2 times 3, that is equal to 6x. Okay, I am now officially done giving you notes. I just wanted to throw that last thing in there, just in case. We'll talk about more rules next week on Monday, all right? So this is the intro to 3.1. Go ahead, read through 3.1 if you can, if you're still struggling with this. Hopefully it makes sense. Office hours, plan on, I'm going to say 12 o'clock tomorrow, okay, tentatively. I will send a message out through B courses later today. Let's talk about your homework very, very quickly here. Okay, let's talk about section 2.8. Here's the numbers that I want to give you. I want to give you number 3. Okay, number 3. Go ahead and find the, that is just matching, you're given the original graphs, the original functions, match them with their derivative graph. Pretty straightforward, pretty easy. Let's give you, let's give you the derivative of, no, tell you what, just do that one. And I want you to find the derivative of, let's do this. So from section 2.8, do numbers 3, all right? Now, handwritten problems, I want you to find the derivatives, okay? Using the derivative rule that we just talked about, right? Find the derivatives of each of the following functions, okay? Let's go with x to the 20th, okay? Find the derivative of x to the 20th, okay? This is one problem, okay? The next problem, I want you to find the derivative of x to the 1/2, okay? You're like, oh no, fractions, the numbers and the letters change, the process is the same, okay? Follow that exact process. So x to the 1/2 power, this is another way of rewriting this, that is the square root of x, okay? And the third problem, I want you to find the derivative of, let's go with 300, oh, I'm sorry. Yes, I will post these. I will make sure to post these on B courses in the assignment section, okay? And I also want you to do the derivative of x to the 34th, all divided by 34, okay? Find the derivative of these 3 functions, okay? Everyone go ahead, write those down. So this is equal to, so these are f of x, right? This is f of x equals, this is f of x equals, and this is f of x equals, okay? Find the derivatives, find f prime of x for 1, 2, and 3, okay? Handwritten problems, yes, I will make sure they're uploaded to B courses. 2.8, go ahead and do number 3. And I'll make it optional. I'll make optional for 2.8 number, let's do number, let's do number 6, okay? So, because I know some people left early, so I'll make number 6 optional. I'm still gonna add it to the assignment. If you don't do number 6, I'm not going to like penalize you for it or be like, hey, you missed number 6. I'll just assume that you just didn't do it because I said it was optional. Sound good? Cool. 5 problems, number 3, number 6, super easy. Numbers 1, 2, and 3, it might take you a little bit of thought, but those are super easy as well. Have a great weekend, everybody. I'm going to stop the recording now.